and it's the second part of this lecture. And I would like to get back to discuss another important point in ab initio methods. It's the electron correlation problem. And by definition, the energy, the correlation energy, yeah, find by this equation, the difference between the energy experimental or the full corrected energy minus between this energy and the energy of Hart-Fock method in the limit of the base set. Okay, but the Hart-Fock method gets 99% of the total electronic energy, and the difference is the electron correlation energy. And the methods to get correlation energy is CI and PPT, couple cluster, and CSCF, MRCI, and so on. But let's think about the electron correlation problem. Is how important is the electron correlation? Let's consider the helium atom. Okay, helium atom has a core with 2 protons, 2 neutrons, and plus 2 electrons outside of the nucleus. And this is the simplest atomic system with electron correlation. Yeah. And the energy, the exact value for the energy is this number in atomic energy. It's the atomic unit, Hart. And the Hart-Fock limit, if you consider a big base set, is this energy here. The difference between the both is the correlation energy. When you convert to 1 mole, 1 mole of helium atoms gives this total energy here. And let's quantify how large is such type of wave. 26 kilocal per mole. Let's talk about the chemical accuracy. Okay, and 2 questions. Let's calculate the energy, the error in delta G that change the equilibrium constant in 10 times. The same question can be do is what's the error in the activation, the delta G activation for a reaction, chemical reaction, that change the kinetic constant in 10 times. If you do the simple prediction, you can find that error is 1.4 pK per mole. The conclusion is the chemistry is in the electron correlation. Okay? But how to improve our predictions? Let's do some estimates for computational demand. If you want to lower or to get better your prediction, you need to choose a method that costs 10,000 times more in computational time. If you have one method that took place 1 minute just to be used, and these methods predicts the energy with the accuracy, bad accuracy, or error in 100 kk per mole. If you replace this method by another that get better prediction in 10 kk per mole, you spend 1 week to solve your calculation, and so on. If you choose a method to that show error in 0.1 kk per mole, you need to wait 20,000 centuries to get this calculation done. And the conclusion is you need fast computers and or efficient numerical strategy to solve the chemical problem. Well, in short words, for the ab initio, you have positive points because they are methods of general use. They don't need use. They don't do not use empirical approximation. All chemical and physical phenomena can be modeled. Chemical reactions, polarizabilities, spectra, vibrations, optical properties, electronic properties, magnetic properties, and so on. But the limitation is this type of methods are applied to a small system or few molecules, okay? Because they demand a lot of computational resources. One strategy to solve this type of problem is to use a semi-empirical theory, and a semi-empirical theory and semi-empirical methods are low-level quantum chemistry methods, and they are based in some key approximations. The first one is you consider that the wave function for the semi-empirical methods is a smaller wave function, because only the most important electrons in a chemical reaction or for interaction with the light are the valence electrons. Yeah, and the core the core electrons are they are like in a frozen core. They don't participate the chemical reaction, and you can consider only in the wave function these valence electrons. Yeah, but you consider the core electrons as a core in this part of the matrix element that compatibilize the interactions. Yeah, the one particle interactions, one electron interactions, and the inner core electrons participate as a potential source to interact with the nuclei and other electrons. One consequence for that consideration is the equations for the Hartree-Fock problem become smaller. The matrices are reduced, and the equation it becomes smaller. Yeah, this is the first approximation you need to do in some empirical theory. The second approximation is consider the overlap matrix in this type of equation, this equation here, because this equation is not solved directly by a simple diagonalization. You need to construct a symmetrically orthogonalized base set to solve this type of equation. And the second approximation in semi-empirical theory is the ZDO, zero differential overlap approximation. And in this approximation, you consider the S matrix, the overlap matrix, as an identity matrix. As such, you need to in the diagonal of the matrix, you have only one, yeah, the number one, and the off-diagonal elements are all zero. This type of approximation cause impact in another parts of the Hartree-Fock equation. Yeah. One part is in the two electron repulsion integrals, okay, something like that, and the only up to 2 centers 2 electron repulsion integral needs to be considered when you do these approximations in the semi-empirical theory. Yeah, because in a symmetrically orthogonalized base set, when you do this type of transformation to solve this equation, naturally the 4 center and the 3 center 2 electron integrals becomes close to 0. And if the semi-empirical methods consider something like that type of base set, you can you able to avoid this type of integrals to be calculated. The third approximation is the integral approximation, and you have 3 levels of approximations. Yeah, is a consequence of ZDO, and you have this simplest one. The simplest integral approximation is CNDO. The first semi-empirical methods are contains this type of approximation. You have an intermediate approximation. The name is INDO, intermediate neglect of differential overlap. And you have the more complete approximation, if you can say like something like that. This is NDDO, and in NDDO formalism of some empirical method, you need to calculate all 2 electron integrals that this type of rule, follow this type of rule. The only restriction is you need to, the A center equals to B center for that part, and C center equals to D center. Center is nucleus, is the nucleus or atom. Okay, and this overlap, these orbitals needs to be centered in one specific atom, And these two orbitals need to be centered in another specific atom. If you have this type of situation, this integral in NDDO method are calculated. Okay. Well, this is the main three integral. It's the main three approximations in the semi-empirical theory, and you can see that you insert some considerations for the equations, and you need to insert some parameters. That name of this theory is semi-empirical because it's not totally empirical. Okay, and if you insert this type of parameters, you need to find the best parameters for your method. Okay, that is the parametrization procedure. There's two options that you do a parametrization procedure, or you adjust by using numerical procedure, or you find these parameters taken from experiments or high-level calculation. The modern semi-empirical methods use the both strategies to find the best parameters to construct your semi-empirical method. That is the pattern of the elements in to assemble Fock matrix. Consider the methanol molecule in this in the diagonal. You need to calculate elements with this type of equation. You have core Hamiltonian here, and this part is the one center elements, and this part is two center elements. You need to consider the atomic orbital center in one specific atom, and the atomic orbital center in another specific atom, Okay. For one center of diagonal elements, you use this type of expression. This is for NDO-like methods, semi-empirical methods. And this expression you use to calculate this part of the Fock matrix. And that part here, the two center elements, because you have one orbital center in one atom and the other element center in another atom, you use this equation to calculate this part of the matrix. Okay, and this step of the calculation, the semi-empirical method, the complexity is something like that, because you need to store the matrix in the memory, and to the second, and you need to. This type of element depends on the two electron integrals up to centers in its theory. Well, the parametrization procedure is the key point of the semi-empirical method. because this is a hard task. You need to choose a response function, a cost function. You need to set a molecular data set. You need to consider properties that you will be used, and you need to consider numerical minimization algorithms. The cost function you need to consider is something like that. Pay attention this part of this function, because this part of function you depends on the parameters that you are changing to find the best parameters. And when you have a situation that these two parts of the equation are close, and you have a minimum in this function, and you method are parameterized. Okay, and the properties you consider in the parameterization procedure is something like that: heat of formation, ionization potential, dipole moment, and this part of the geometries. And you need to put also a weight here, because if you want to pay more attention for a specific system, and you insert higher weight here, and this function you will guarantee that this type of system will be a nice will be better reproduced in this in your prediction. Well, this is a tree that's count the history of semi-empirical theory time. We start here with equal theory in 1930, and you have this type of improvements in this theory, and you have a branch of semi-empirical theory with CNDO, INDO, and NDDO, and this framework you can using this framework you can find these modern semi-empirical methods that known as Dewar type methods or Dewar type semi-empirical methods. Okay, and this type of methods gave for us new directions for semi-empirical methods. Well, I will show some new semi-empirical methods with emphasis on the study of biomolecules. The first one is the semi-empirical method that I developed in my PhD. And today, the RECIF Model 1, RM1, is the same like AM1, is based on the NDDO theory. And now this method has 24 atoms, the parameters for 24 atoms, and the 24 atoms, and the atoms are C, H, and O, because the most compounds in organic chemistry are have this type of atoms. If you consider the biochemistry, you need to consider the P, phosphorus, and sulfur atom. If you want to be drug design, want to do drug design, you have to consider the F, fluorine, chlorine, bromine, and iodine. And if you want to do predictions about photonic and medicine, you need to consider the lanthanides. Yeah, and that's the paper we published for the RM1. Okay. Well, sorry. You can find some improvements of the RM1 and some details in this website, but a special result for RM1's method is you can find on this figure that shows the prediction of the entropy of formation, for the entropy of formation. In this X, you can find the experimental results. In this X, you can find the RM1 predictions for the entropy of formation. Okay. If you pay attention in this equation that fits this data, you can find that the angular coefficient is close to 1, and the correlation coefficient is close to 1, and the linear coefficient is close to 0. And that is, if you have a prediction by using RM1 for the entropy of formation, that prediction is close to the experimental result. This is a comparative result, including early semi-empirical methods. And that time, RM1 is the best one to predict entropy of formation. Today, many improvements on the RM1 that you can find in the literature. That counts hydrogen bonding, and that journal you can use improvements of the RM1, and the guys did a good job to set some additional parameters for the RM1 to correct some hydrogen bonds in this type, and their results to show that their improvements. For salvation, yeah, an extension of MST continuous salvation model to RM1 semi-empirical Hamiltonian. You can find that results in this paper. For vibrations too, harmonic vibration frequency scaling factor for new and DDO Hamiltonian, RM1 PM6. You can find this coefficient to you scale the vibration frequencies. It's a common procedure in quantum chemistry. Well, and especially for the lanthanide ions, we have a Sparkle model, yeah, This is a simplification. It's a model, a simple model to allow the ground state calculation for lanthanide complexes. That is all publication for the Spaca model. And you have parameters for PM7, PM3, RM1, AM1, PM6. Okay. You can find many tutorials in this website. It's totally free because you can find the parameters for all these methods, and you can insert these parameters in your code, and you are invited to access this web page to find this type of improvements. Well, the next semi-empirical method that I would like to show you is the PM6. PM6 is a method. It's a kind of the theory is completely the same, almost the same of RM1 or AM1 or PM3, but the big difference is that PM6 is parameterized to 7 elements. This is a huge improvement for the semi-empirical methods, and the first semi-empirical method that has a lot of elements, parameters for 7 elements, but in the comparison with RM1 in that paper of PM6, it's a bright light. Yeah, the Professor Stewart said that his RM1 was functionally identical to AM1. Statistical analysis showed that RM1 was more accurate than any of other NDDO methods, and therefore was the method of choice for modeling organic compounds. Okay, it's a good well, we can find also this type of method, OM1 and OM2. I think there is OM3 also. But this type of method, orthogonalized method, that's the paper. Professor Walter Thiel has started correction to avoid some deficiencies caused by ZDO approximation. There are 2 problems with ZDO approximation. ZDO approximation has a strong impact to the torsion angles for conformational analysis and in the ionization potential. Yeah, because remember I showed this equation for you. In Hartree-Fock-Rutan approach, we solve this matrix equation. It's generalized eigenvalue equation, because you need to transform this equation to avoid this type of matrix. But the semi-empirical consider the transformed Fock matrix in this symmetrically orthogonalized phase molecular orbital. Yeah. Semi-empirical theory consider the Fock matrix when they did the ZDU approximation as the transformed Fock matrix. And the problem is you avoid the S matrix, the overlap matrix, and this approximation cause some problems in your description for your molecule. And a way to you do some correction about this type of problem is to consider the S matrix again. Yes, you insert some terms that are that are based on the S matrix in your mainly in the one electron Hamiltonian, something like that. In the final equation, you need to consider in this type of method, OM1 and OM2 is something like that. If you pay attention in this type of equation, you see that the this summation consider three center terms, yeah, and these three center terms you make better the conformation analysis, and you solve that type of problem. Consider additional terms that depends on this three atoms, yeah. But another problem is the splitting of the molecular orbitals. If you consider the ZDU approximation, is something like that. And when you consider the effect of the S matrix in this splitting of molecular orbital, the real situation is the ligand molecular orbital is the level of the ligand molecular orbit is lower, the same place, but the anti-ligand is completely different. And if you consider the S matrix, you will be able to correct this type of excitation, yeah, and you correct the ionization potential too, because you need to consider the difference between the two levels better, yeah. The another problem involves the semi-empirical methods, and in general for the low-level quantum chemistry methods, is because they fail to describe non-covalent interactions. And non-covalent interactions are too important to you describe biomolecular systems. Okay, and the strategy to you consider this type of interaction is to insert some correction term that will count for this type of interaction, something like that, and you have your energy calculated by your method, and you make additional correction to count this type of interaction. And this strategy was applied for many semi-empirical methods, and this type of correction you can find in many programs and many packages we have in this area. Yeah. The most recent semi-empirical method is the PM7. PM7 corrects some NDDO errors, okay, especially for solids and crystals, but differently from the other semi-empirical methods, PM7 consider the non-covalent interaction in the parametrization procedure. Okay, and this method is I consider this method as the best method to you calculate non-covalent interaction. That paper is a very interesting paper because the paper makes some comparison about semi-empirical methods and molecular force field to describe common systems in biology. Yeah, and the conclusion of these guys is the force fields are suitable to protein dynamics, but the atomic charge are prefixed, and there is no explicit treatment of the electrostatic polarization and charge transfer. Yeah, but a point here is very important because the guy said, in contrast with the computational chemistry intuitive idea that more expensive a method, the better its accuracy, their force field, the amber force field, results were more accurate than most semi-empirical methods, with the exception of RM1. The reason is simple. Is when we parameterize the RM1 method, we consider in the parameterization set some example of non-covalent interaction between amino acids, small polypeptides, and interaction with DNA and something like that. And this is a good result for us. Well, if you have more interest in learn about semi-empirical methods, these chemical reviews is very good material to learn about the new semi-empirical methods, and you can find the discussion about many semi-empirical methods to be used in biochemical applications. Okay, and short words, you can find the positive points for semi-empirical quantum chemistry methods is that for most methods the parameters are atomic. This is an important point because in the force field you have 2 atoms parameters, 3 atoms parameters, 4 atoms parameters. This is about very complicated to find this type of parameters. All chemical and physical phenomena can be modeled, the same thing like ab initio methods, but the limitation is the accuracy is insufficient. The parameterization procedure is quite difficult, and most semi-empirical methods don't have parameters for all the atoms in the periodic table, except PM7, PM6, and PM7. Well, I will consider in this part of my lecture the high-performance computer for semi-empirical method, because it's an important point that we consider in my research group. If you pay attention with the SCF algorithms, you can find the same scheme that I showed you yesterday, but this slide shows you the complexities for the semi-empirical methods in each part of the algorithm. If you consider semi-empirical methods in this part of the SCF algorithm, the complexity is something like that. And that part, for the diagonalization of the Fock matrix, you have the same complexity to the ab initio and DFT methods. And that step of the semi-empirical methods is the step you need to consider as candidate to be accelerated. And for the ab initio methods, that part is the most important to you to be accelerated. And that's some complexities about the linear algebra procedure, diagonalization cost and the 30 to the 30, matrix multiplication are the same, and so on and so on. You can find CI calculation is very high demand computational method. But the key point is many of these procedures are called many timers for iterative algorithms, and the solution for these tests is to use high performance computing. And today we have GPUs, yes, and in about I think 2007, GPU was present to the scientists, and in the for the chemists, theoretical chemists, we use to accelerate some specific parts of the algorithms, especially for ab initios and molecular dynamics simulations, and we can try to accelerate semi-empirical methods. Okay, and for semi-empirical calculation, there is one traditional code. This code is MOPAC. You use them in this course, maybe. And MOPAC is a big code. It has a lot of lines of code, and it's very difficult to find the points we are need to improve this code. And our objective is to accelerate to accelerate semi-empirical calculation in MOPAC by using GPUs. And we published this paper where we detail our strategy to get that paper. And in short words, what we done is we did was to find specific parts of the MOPAC code that counts for matrix multiplication, and this is the same matrix multiplication considered electron density matrix as a symmetry matrix, and you can use a specific procedure in the high performance library for GPU, and we replace that operation in our operation by its the equivalent in GPU in the equivalent of the GPU version. Yeah, we use QBLAS library to do this type of operation, and for that you use this type of this silver protein in the QBLAS library. And for the full diagonalization, we use Magma library and Intel MKL for CPU version. And if we compare the performance to the legacy code of Mopac, you got some improvement, yes, some speed up when where your new version of Mopac, the parallel version of Mopac, becomes for that system, it becomes 35 times faster in comparison with the single core run. Yeah. For that system, it's a simulation box of methanol. The speed up was higher, 54 times faster. You have considered other systems, fullerenes and small polypeptides, and you have improvement for the geometry optimization step in the Mopac, and we noted that the larger the system, the highest the speed up. When you have the system like that, I think it's a fullerene, 60 atoms. If you consider the largest system, you have higher speed up. Okay, and the same thing happened with the polypeptides, small polypeptides. Yeah, become faster. And we have add some improvement for the vibrational frequencies calculation for large molecules on GPU. And the same thing, you can find the highest this system, the largest the system, the highest the speed up. Okay. And now Mopac, in Mopac web page, you can find a link to my research group. Give some credit for our work. And in the NVIDIA web page, you can find a link to the Mopac in 2012, and I think 2016 is the same thing. In the final part of my talk, I would like to show some application of quantum chemistry, especially for the semi-empirical methods in biomolecules. This slide is a scenario for when you decide to use this method or this another method. If you consider one system, the the most used methods, the most suitable, the method most suitable to be used are the ab initio methods, and the semi-empirical methods are candidates to be used when you have a large number of small molecules and a big one. Okay. That slide I show the scenario of the quantum chemistry methods until in 19. Yeah, the organic chemistry. If you study some system in organic chemistry, the methods that you used were semi-empirical one and the DFT. And if you study biochemistry system for biochemistry, you used molecular modeling, molecular force fields, yeah, to study this type of system. But now the scenario is completely different. If you need to study molecules in organic chemistry, the best choice is to use DFT methods. And now in biochemistry, you are able to use semi-empirical methods to study this type of system. And that slide is something like that previous slide. When you have many calculations of many small molecules, you can use semi-empirical methods, something like that. And when you have a giant molecule, you able to use semi-empirical methods too. And when you use quantum chemistry calculation coupled to a molecular dynamics simulation method, you can find the electronic structure of your material. This is an important difference when you use only force field to do molecular dynamics. But the question is, what are we able to do with a wave function and electronic density spread over millions of atoms? I consider that paper as a good paper to answer that type of question, because in this publication, the researchers consider two calculations for this type of protein. They did calculation in gas phase and the calculation in this solution phase, okay, aqueous phase. And they noted that when they consider the solvent, the frontier molecular orbitals can be localized in the active site of the enzyme. Okay. And in a recent paper, I think the same guys considered a small set of the PDB containing 112 non-redundant enzymes from PDB database, and they did some semi-empirical calculation with some considering the electronic structure for all these enzyme, And this enzyme, from these their results, this enzyme can be classified as enzymes that have extremely localized molecular orbitals in the active site and higher delocalized molecular orbitals, as such, molecular orbitals spread in all molecule of protein, and a third set of enzymes has medium-sized molecular orbitals. And when they can see this type of enzymes, they found that this type of enzyme are to have high specificity, enzyme specificity. And I think these finds are only possible when electron structure methods are applied to the problem. Well, in my group, we can study some aspects of the protein folding problem. And one important aspect of the protein folding problem is to find an efficient and accurate way of sampling a very large conformation space by using energy function that can discriminate accurately between the native state of that protein and the non-native state of the protein. And you have a situation like that, that you have a huge number of conformation in this level of the funnel, free energy funnel, and one specific native structure quite different in free energy from this huge number of conformation. Well, we selected 33 decoy sets from Zeng Lab. Yeah, we have downloaded this set. In each set of in each decoy set, you have about 500 conformations. That table shows you all the protein that we consider in that study. You can see that it's around 500 or less or more. And well, like that. Sorry. And we propose an algorithm to select when we calculate this function. Yes, this function. We select. We discriminate the native structure from the another structure, and we consider that the native structure is as an outlier in this ensemble of conformation, and we assume that the random ensemble of conformation have a Gaussian distribution of enthalpies, the enthalpies of formation calculated by using semi-empirical methods, and we proposed algorithm when you have a lot of conformations, you decide which one is the native structure. Our algorithms works in this way. you have to input the decoy set. You have after that you have to calculate the entropy of formation by using semi-empirical method, and you take the mean of the entropies and the standard deviation too, and you ask if are there upper deviants. If you have conformation with energy up this limit to standard deviation up, you throw away this conformation and do the same thing in an iterative procedure, and the working of algorithm is shown in these figures. Here, in the first interaction, you have too many geometries with energy up to the standard deviation here. For the another step, you can note less. Another step, less more. When you goes to the final, you have any no conformation up to this limit, and you look 3 standard deviation below. That is the probably that is the native structure, yeah. And we have applied this algorithm to these all molecules, all these protein, and we were able to find that all, if you consider the PM7 semi-empirical method, all these decoy set, except one, that you can find the native structure, the conformation, the native structure as a native structure. Yeah. For that, we consider 4 semi-empirical methods. Almost all of them have non-covalent correction, except PM6. And we did one SCF calculation considering the solution, aqueous solution, by using Cosmo model. 33 proteins, each contain about 4 or 5 decoys, which totalize around 61,000 QM calculations. And that is, these results were published in this paper in 2016. And I finished my talk. I would like to thank for the founding source in Brazil, yeah, and thank you very much for watch my lecture for the semi-empirical methods. Okay. Thank you very much.
Do you have any questions?
Yeah, so I have a question about your protein folding. So in your protein folding case, we only know the initial and final, and we don't know the folding pathway in this case.
This?
Yeah.
This problem?
Yeah. Can you
That's
know
problem.
so can you know the
Mm.
native structure
Mm.
and the unnative structure, how it folds, like folding pathway,
No.
just the
No.
initial and final,
Just the energy, just the energy.
and then
Not the mechanism, not this or consider, not this. Just the energy, just to find if the entropy of formation is a good score function to discriminate the native structure for the anothers. Just for that. Something like I think it's cast competition. They developed some methods to find the native structure from the primary sequences. Yeah, and can be the heteroformation can be used to do this type of thing. You know. Yeah. Question?
Do you think including, like running dynamics and including some sort of entropic contribution would improve the model?
No.
No.
Entropic contribution is very quite difficult to consider in this type of calculation because you need to count the vibrational parts of the entropy contribution. In vibrations, if you need to calculate the vibration for this type of protein, small proteins with 1,000 of atoms, maybe. But even in this case, the calculation to you count the entropy factors are complicated because the vibration, you need to diagonalize a small, big matrix. And it's difficult to